Okay, so now we're looking at part E, 2 cosine 2x plus 1 equals 0. So notice, well, I should mention in the problem I didn't put parentheses here. If there's no parentheses, then you assume that this is the input and not 2x plus 1. For it to be 2x plus 1, you would have to have the parentheses. If there's no parentheses, then it's just the one, factor after the function. I probably should have just put parentheses in there to be more clear. Okay, so we have a double angle in here, so there's going to be a period change. We'll deal with that later. Right now we just want to isolate the cosine part, so we can move this 1 over and divide by 2. We get cosine of 2x equals negative 1 divided by 2. So now in this is very similar to what we did up here, in H and I, but the difference is we only want solutions in 0 to 2 pi. So you might be thinking, well, cosine is negative in quadrants 3 and 4, or excuse me, 2 and 3, right? 2 and 3. So I'd only get 2 pi over 3 and 4 pi over 3, and that's it, and I'm done. But things get changed because of this double angle. So it's 2x that would equal 2 pi over 3, and it's 2x that would equal 4 pi over 3, which changes what x is, right? And we're trying to get all the way down to x. We're solving for x. Now, because of the period change, we actually get more solutions than just these two. This is a little tricky, but if you think about y equals cosine x versus y equals cosine of 2x, this has a period of 2 pi. This has a period of pi. I did it again. That should be 2 pi, and this is 2 pi over 2, which is pi, right? So if you think about the graphs, for y equals cosine x, you've got one cosine wave from 0 to 2 pi. So this thing equals negative 1/2, right? 2 times from 0 to 2 pi. But when you graph y equals cosine of 2x, you get 2 cosine waves from 0 to 2 pi because the period is cut in half. So this, I'm going to use red here. Not my best cosine wave, but you get the idea, I hope. Right? This cosine wave occurs 2 times, so you get 1, 2, 3, 4 solutions, 4 numbers where cosine of 2x will equal negative 1/2 in the same interval. So we actually come up with twice as many solutions here. The easiest way to come up with these solutions is to initially treat this, when you're solving this, like you're finding all solutions. So I'm actually going to add the period 2 pi k to both of these. Then multiply through by 1/2. So x, that's to get rid of this 2, right? So x equals pi over 3 plus pi k. So I took everything times 1/2, or divided by 2 if you will. And then x equals 2 pi over 3 plus pi k. So of course this is my new period. So notice this is my pi over 3, that's that one, red dot, my 2 pi over 3. So now this is all solutions, right? All solutions. But in 0 to 2 pi, which 4 do I want? Well, pi over 3, 2 pi over 3, and then add pi to this. Pi is 3 pi over 3, which would give me the 4 pi over 3. and then add pi to this one. 2 pi over 3 plus 3 pi over 3 is 5 pi over 3. Those are the 4 solutions which I showed graphically with the red dots there. Right? So because the period is half as long, there's twice as many solutions. So you have to be careful about that. So I recommend treat it like you're finding all solutions and then pick out the ones that actually fall in the interval you're looking for. So again, this one was pi over 3 plus pi. This one was 2 pi over 3 plus pi. And if you keep adding, I should point out here. So this one, you know, this is our pi over 3. This is pi over 3 plus pi. Pi is 3 pi over 3, right? So that gives us a 4 pi over 3. That's that one. If you add pi to that again, I knew we only needed the 4 solutions because of the graph, but I was like, say I didn't know that. So what you would do is you keep adding the period until you get outside of 2 pi, right? So that you don't want to include that in your solution set because it's bigger than 2 pi. So sometimes you end up with, you know, if this were a 5x, you'd end up with 5 times as many solutions. So 10, originally you'd have 2 solutions, right, for cosine. With a 5x, the period is a fifth as long, and so you're going to get 5 times as many solutions. So you'd have 10 solutions to that. Okay, let's go on to the next one, F. Let's see, square root of 3 tangent of 1/2 x plus 1 equals 0. So you can see the tangent expression here. Isolate that first. So we get negative 1 over the square root of 3, which is negative square root of 3 over 3. So tangent, negative in quadrants 2 and 4. Reference the angle here is pi over 6. So you're going to get 1/2 x equals 5 pi over 6. And then 11 pi over 6 in quadrant 4 is actually pi units away. So you can just add the period pi over k once. Or you can add 2 pi over k, but then you need the other statement, 11 pi over 6 plus 2 pi over k. I'm just going to do the one statement because it's less work. Alright, so if I know 1/2 x has to give me 5 pi over 6 or 5 pi over 6 plus the multiple of pi. So now I'm going to solve for x by taking everything times 2. So x equals, so I take 5 pi over 6 times 2, I get 5 pi over 3, right? The 2 goes into 6 3 times, plus 2 pi k. So the period actually gets longer because of the 1/2, right? So you've got a stretched out period. In 0 to 2 pi then, we're just going to get 5 pi over 3 because when you add or subtract a multiple of 2 pi, you're going to be outside of 0 to 2 pi. So, whoops, that's 3. That is our only solution, okay? Now, I'm going to add an extra example here. So F, well, we'll just call it example. If I had changed, let's just use the same basic example, but I'm going to change this to 4x in here instead, okay? So we'd solve it the same way, but we got 4x, right, equals negative 1 over square root of 3, which is negative square root of 3 over 3, okay? So then you would say, okay, well, 4x equals, it's the same thing we got here, not doing anything different yet. We still need, the solution in quadrant 2 that gives us negative square root of 3 over 3. Add pi over k to that, because that's a period. But now I'm going to divide everything by 4. So x equals, so the period gets cut in fourths, right? In a quarter, if you will. So notice 5 pi over 24 is a lot smaller than 5 pi over 6. So now I need to come up with just the solutions in 0 to 2 pi. So initially in 0 to 2 pi, if I didn't have a multiple angle here, I would just have 5 pi over 6 and 11 pi over 6, just those two solutions. But because of the 4 and my period shrinking up, I'm going to have 4 times as many solutions. I'm actually going to have 8 solutions here. And this is how you're going to come up with them. You take the 5 pi over 24, that's your first one. And then you keep adding the period. Now these don't have a common denominator, so I would go in the margin here and find a common denominator, which is 24. So I want to take this times 6 over 6. So I get 6 pi over 24. So I'm going to add 6 pi over 24 to 5 pi over 24. And because I have a common denominator, now it's easy. I just get 11 pi over 24, right? 5 plus 6 is 11. Now I just keep adding this to the next solution. So 6 pi over 24 plus 11 pi over 24 is 17 pi over 24. Sorry, I'm going to need water. 17 pi over 24 plus 6 pi over 24, 23 pi over 24. I've only got 4 of the solutions. Notice this is still smaller than pi. 23 over 24 is less than 1. Keep adding. Now I've got 29 pi over 24. Add again. 35 pi over 24. None of these reduce, but if they did, I would reduce them. Right? Like if I got 22 pi over 24, I would reduce it to 11 pi over 12. So you do want to simplify if you can, but these don't. Add 6 again. Now we've got 41 pi over 24. Add 6 again. 47 pi over 24. And I did say we would get 8 solutions, right? Notice now if I add 6 pi over 24, 53 pi over 24. 53 24ths is bigger than 2, so this is bigger than 2 pi. So if you keep adding that period, eventually you get kicked out of the interval you want. So these are my 8 solutions that I was talking about. Okay, so you just keep adding the period, get a common denominator, add the period until you get to, okay, now that's too big, I'm done. Okay, sorry, I need water and all I have is coffee, so I'm gonna go grab some water and then I'll make another video. Sorry.